Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley. And this is module 25 in a series that we're recording for the course EECS 221A, which is linear system theory. Today we're going to start talking about the concept of Jordan form of a matrix, but we're going to introduce it through a couple of things first. And the first concept, and so today's module is going to focus on two things: A-invariant subspaces and direct sum of subspaces, which we're going to need to think about Jordan form. So what do we mean by an A-invariant subspace? What does it actually say? So A-invariant subspace. We know what a subspace is. Subspace of a vector space. So what does it mean to be A-invariant? And A here is our typical A. It's an n by n matrix of reals. And it's we can think of it as the matrix representation of a linear map A. So we've got our space U, vector space V, linear map A, and its matrix representation capital A. We say that a subspace, let's think about, just a vector space. We can think about the vector space V, or let's use the vector space U. So a subspace M of U, of the vector space U, is said to be A-invariant, if for all vectors u in M, AU also belongs to M. Okay, so this could be the linear map A, or it could be its matrix representation. It doesn't matter. So it says that any vector has the property that if you operate on that vector by A, you stay within that subspace. Okay, so we often write this as A operating on the subspace M is a subset of M. You get back into the same space. So you can't get out of that space by operating by the operator A. Okay, so some things that we know and love, some spaces that we're familiar with, are all A-invariant. So if you think about the following examples. So the first example is that the null space of A is A-invariant. And these things are really easy to show. Okay, so the definition of A-invariance is simple, and so showing something is A-invariant is particularly simple. All you have to do is take any vector in that null space, and since it's any vector, if you show that A times that, or A operating on that vector is also in that space, then you've shown in general that the space is A-invariant. Okay, so let's take any x which belongs in the null space of A. So that means that AX is equal to 0. And now we want to be able to show that AX is also in the null space of A. So let's think about AX. Is it in the null space of A? So question mark, is it in the null space of A? Well, to check that it's in the null space of A, we just have to see what AX is. But AX is equal to 0 by definition, so this is equal to 0. Therefore, AX is in the null space of A. Okay, so it's very simple to show these. So you can show all sorts of other things. You can show that the range of A is A-invariant, You can show that if you consider lambda I to be an eigenvalue of the matrix A, so let's continue our examples up here, and let's just write them down. So that's 2. Here's example 3. The null space of A minus lambda I is also A-invariant. That's a little bit more involved, but again, it's easy to show. So here, this is an eigenvalue. Lambda I is an eigenvalue of A. So it belongs in the spectrum of A, is how we denote the set of eigenvalues of the matrix A. More generally, suppose you had a matrix, or suppose you had a polynomial function of the matrix A. So let's write that out as A to the k plus alpha 1 A to the k minus 1 plus alpha k minus 1a plus alpha ki. Okay, so some polynomial function of the matrix A, then the null space of that polynomial function of A, which is a matrix, is also A invariant. So the null space of P of A is A invariant. Okay, and finally, if you had two A-invariant subspaces, so suppose M1 and M2 are both A-invariant, then you can say something about operators on those subspaces. So if we define M1 plus M2 to be the set of vectors x in their parent space U, so the set of x in U such that x is equal to x1 plus x2, where x1 belongs to M1 and x2 belongs to M2. So xi belongs to mi. Then we can think about this as the sum of two subspaces. Then we can show that this is A invariant. So M1 plus M2 is A invariant. Also, if M1 and M2 are A invariant, their intersection is going to be A invariant. So M1 intersect M2 is A invariant. M1 intersect M2 is also A invariant. Okay, another combination, M1 union M2. So if you had two subspaces, M1 and M2, they're both A invariant. Can you say anything about the union of M1 and M2 being A invariants? And the answer to that is no, because we don't even know from our earlier work in subspaces if M1 union M2 is a subspace. We can come up with counterexamples where the union of two subspaces is not a subspace of the parent space U. Okay, but we can, if we define sum of subspace and we define intersection of subspace as we do, then those are going to be A invariant if their component subspaces are A invariant. Let's talk about one more thing in this module, which is the concept of direct sum of subspaces. Now, this doesn't necessarily have anything to do with A invariants, but we're going to be using it. And we've talked about the sum of subspaces. What is the direct sum of subspaces? Okay, so let's erase everything here and talk about direct sum of subspaces. Okay, so direct sum of subspaces. Again, we're starting with this structure, which is a subspace. It's a vector space in itself, which is a subset of a vector space. So we say that V is the direct sum of subspaces M1 up to Mk, and we use the following notation for direct sum. Okay, so this is the direct sum of subspaces M1 up to Mk. If for all vectors x in V, x has a unique decomposition in terms of elements in each of those subspaces. So that means that we can say there exists unique values, vectors, xi, and each of the xi's belongs to an mi for I equals 1 up to k, such that x is equal to x1 plus x2 plus xk. Okay, so it's a little bit of a roundabout definition. We define direct sum in terms of the ability to take any vector in V and write it in a unique way in terms of elements from each of the individual spaces. So from this definition, though, we can come up with some properties of the direct sum. So we can think about the direct sum as kind of a generalization of linear independence. So we can see that if this definition holds, so if V is the direct sum of these subspaces, then we have that, so let's write it as this way. Direct sum in the sense that we've just defined implies that mi intersect mj must be trivial. The only thing in their intersection is the 0 vector. And it also implies that v is equal to the sum of those spaces. So I can just remove the direct sum and write it as sum plus mk. Okay, so direct sum implies that direction. So the first thing is that if you have that v as the direct sum of those spaces, by consequence of this definition, you cannot have anything in the intersection of any of those subspaces. If you could, then you wouldn't be able to get a unique decomposition, because you could always choose another decomposition and such that you use the thing in their intersection, and that's not possible. Interestingly, this is not necessarily true. So while direct sum implies these properties, those don't necessarily imply that it's the direct sum. Okay, so we've introduced in this module the concepts of A-invariant subspaces. So an A-invariant subspace is one in which if you take any vector in that subspace and you operate on that vector by A, you'll remain in that subspace. And we've also introduced the concept of direct sum as being a generalization of linear independence for subspaces. Now in the next module, we're going to move on and use these to try to construct the Jordan form of a matrix. Thanks very much.